And maybe just a quick bio of Mussawar Ahmad, so we get to know who the real speaker is. He's from the University of Warwick with the Automation Systems Group and a third-year PhD student looking into his thesis that's titled Cyber Physical Representation of the Dynamically Reconfiguration, or is it reconfigurable fuel cell assembly systems? Right. So this is just what he's doing by way of, it's quite technical words. I'm sure most of us really can't digest it, but with the presentation coming up, pretty much I'm sure we'll be able to understand whatever he's doing. So, okay. So you've got 20 minutes of presentation and 10 minutes of questions. So
10 minutes of questions.
Yeah,
okay.
Can we work within the time frame?
Yep. Okay, perfect. Okay, start from everyone. So yeah, thanks for the introduction. I'm Mussawar Ahmad. I'm University of Warwick, and the title is "Where are hydrogen fuel cells today?" Is this going to work? Yes, it is. Okay, so just a very quick background as to the wider context. So should I stand that side? Is that better? Yeah. Okay. So the background is to say, well, okay, there's a lot of places you can apply fuel cells, but the area that I'm looking into is a lot to do with automotive. So you have a couple of numbers. So you say currently there's about 1 billion cars in the world. By 2050, the estimates say it might be 2.5 billion. So it could be even more than that as cars become cheaper, as more people are able to afford cars. Vast majority of cars run on gasoline or diesel, and these types of engines are not efficient at all. So 75% of what you put into the tank is exhausted as heat, either through the exhaust or through the cooling jacket on the engine. So in order to meet the legislation that governments around the world are trying to reduce traffic or reduce the effects of traffic like that and preventing smog like that in China, is costing the automotive companies a lot of money and a lot of time to implement these technologies. And that's why you have cases like VW, who have tried to circumvent the system because it becomes economically unviable at a point, because you might be able to implement the technology, but the car is going to be very expensive and you're going to be outcompeted by your competitor in terms of cost. So the overview of the presentation is to tell you what fuel cell is, so how an alternative energy generation device can or could replace the internal combustion engine, where they're used currently, and why aren't we using them today? So where are they, sort of thing? Because hopefully by the end of the presentation you're going to think they're great. And so there's the first problem is, okay, what is a fuel cell? There's many different types. So I've got 6 there, but even now there's a new one that somebody's come up with which uses a slightly different operating principle. So people are coming up with new architectures all the time. But these are the common ones. So if you looked in a fuel cell textbook, this is what you would find. And these are used across the power range. So what you've got there is a power in watts. So you can develop tiny little ones for maybe your phones or your laptops, and go all the way up to power generation to compete with big power stations. And different fuel cells fit in different areas. So the most flexible you should be able to see from there is the Proton exchange variant, and that's the focus of my research. And the main difference between these fuel cells is usually the electrolyte, which is I guess a membrane in the middle of each cell which separates the anode and the cathode. Another difference is a fuel, so what you feed it with, and thirdly it's usually temperature as well. So something like solid oxide, molten carbonate, they're super hot, Proton exchange membrane fuel cells, we run them about 80 degrees. There's higher temperature versions as well, but they're not much more than 130 degrees centigrade.
Sorry. But the car batteries are fuel cells?
No, that's a battery. That's
So what's
there's
the
a
difference then?
So I'll go over that, yeah. Okay, so operating principle. So with a battery, what you do with a battery is you charge it. You have a store of chemical potential energy, and you put a load over it, and you discharge it. And once it's been discharged, you either have to recharge it or replace the battery. That's not how a fuel cell works. A fuel cell is much more similar to something like an engine, where provided you keep providing it fuel, which is why it's called a fuel cell, it'll keep going. So how the architecture of a vehicle, for instance, would be very similar to what you have in a car today. So you'd have some power pack, so currently that's an engine, you could replace that with a fuel cell. You'd replace the hydrogen fuel tank, you replace the gasoline or diesel fuel tank with a hydrogen tank. You'd go up to a station, you'd plug it in, you'd fuel up with hydrogen. So it'd be a very similar principle to how you would use an engine. So that's the major difference. So what you have, for instance, the issue with batteries, especially in automotive, is there's now actually a term that people have come up with, which is called range anxiety, which means that the battery does not give you the range that you actually need, or people don't feel that the battery doesn't give you the range you need. So on average, people don't drive more than 100 miles a day, and many electric cars can get you 100 miles a day, but people will still not buy an electric car because they think, what if one day I need to drive more than 100 miles, what do I do? So that's the problem, whereas a fuel cell powered car, you can go and refuel it in minutes rather than waiting hours to recharge. Okay, so specifically proton exchange membrane fuel cells, which is what I'm working on, where are they used? And potentially they can be used pretty much anywhere. They are, like I said before, they're the most flexible type of fuel cell, partly because they're reasonably low temperature, partly because they have something called a solid electrolyte. So if I'm able to go back a slide. Yeah. Yes. So what you have in the middle where it says catalyst and PEM, that's a solid electrolyte. Other fuel cells have a liquid electrolyte, which makes it a bit of a nightmare. So they are nice and simple to make. They're nice and simple and safe in terms of temperature. So that's why one of the main reasons why you can see them being used in so many places. Okay, so just to give an idea of where they are used today, so that you can put them in little cars. Nissan and Honda and Toyota and Hyundai are putting them in big cars. Mercedes is going to try and put them in big cars. You have aerospace applications. You have backup power and off-grid applications. One of the major applications today is backup power for the servers of companies like Google and Facebook, and also another major one is material handling. So in America you have Walmart, who have huge warehouses where they're moving food and other products around, and usually that would either be usually it's a battery powered forklift truck, but people are now moving to fuel cells because you don't have the recharge issues. Okay. So why are we using them? So most of the time when you say why are we using their technology, it's usually because it's very expensive, and the same is true for fuel cells. So there's three major areas of cost for a fuel cell. One aspect is its durability. So an engine. So I'll keep comparing everything to engines because that's a good benchmark. So an engine in a car is designed to last 5,000 hours, and the fuel cells, well, some people say we can get, so for instance I went to Japan a couple of weeks ago, I spoke to Honda and Nissan, and they said, well Nissan said yes we get to 5,000 hours, but that's in nice lab conditions in real world application. I don't think anybody really knows how far you can push these things. Power density is a major issue, and the reason that is because so power density means within a given volume or within a given mass, how much power can you produce? And with a fuel cell, the way that the way that it operates is you have to have platinum catalyst on both the anode and on the cathode, so both on the plus and the minus, and platinum is very expensive, so you want to minimize that, but the moment you start minimizing that, you lose the power. So that's the major problem with fuel cells. That's where a lot of the cost come from, that's where the majority of the cost come from. And the final aspect of the fuel cell is manufacturing. So how do you make them? How do you make the components? How do you put the components together? How do you check that you put them together correctly? So all of the manufacturing related issues which most of the people working on fuel cells are not looking at. So they're looking at the first two issues, they're not looking at the third issue.
Sorry, when you talk about power density, what typical numbers are we looking at?
Okay, there's a massive range, to be honest. I think popular numbers are about 2.5 kilowatts per litre to maybe 3.5 kilowatts per litre.
Okay. That compared to something like 100 brake horsepower per litre for engine.
Well, I don't think you can get 100 brake horsepower per litre from an engine. A litre is not much space. So.
Good point, I think, like if at least at the sport end, if you're looking at 3 litre engine, maybe with a bit of turbo, you can definitely get 3 litre.
Oh, I see. So yeah, from the combustion chamber perspective, yes, but the engine is obviously a big pack. Yeah.
But it is supposed to run, the vehicle is supposed to be run by electrical motor.
Yes, absolutely, yes.
Which has more space to occupy the fuel cell space and the motor, and the size will matter again.
Size will matter at the end, yes.
What is the size of the fuel cell which can, you talk about the manufacturing.
Yes.
Yes, so what is the general size of fuel cell and then the electric motor that will drive the car?
Okay, an 80 kilowatt stack, it's not actually that big, it's probably about that wide, about that high, about that deep.
Okay, so both the fuel cell and the motor would become equivalent to the engine size?
Yeah, I think it's really hard to define a system, because you have to think about the system. So you have a hydrogen tank, which is really big, even though gravimetrically hydrogen is energy dense, but volumetrically it's not.
Yeah.
So you have a massive hydrogen tank as compared to gasoline. So what are you comparing? That's what's really hard to do.
Yeah. One other thing about hydrogen is highly flammable. So what
Yeah.
is expected?
Yeah, absolutely. So the durability issues are mostly cold starting and carbon corrosion. So one of the components on the fuel cell, well, many of the components within a fuel cell have a lot of carbon in them. So solutions to cold starting is we put in heaters. So a fuel cell car will have a big fat battery inside it and a heater. So when you start the car, the idea is the heater heats everything up super quickly. All of the ice that was inside the fuel cell, because the fuel cell produces water, will melt, and you won't damage the fuel cell on startup. So that's one thing, and it's become very quick. So currently, even diesel engines have something called glow plugs inside them, and 10 years ago, 15 years ago, you'd actually have to turn the key for a little bit, wait until the glow plugs had done their business, and then ignite. Otherwise, the engine wouldn't work very well. But now, obviously, you don't really. If you start an engine on a diesel car or start the engine on a gasoline car, I think 99% of people don't know that there's a difference in the way these things start out. So that's the same thing has now been achieved with fuel cells. You can cold start extremely quickly, and you wouldn't notice. And the other one is carbon corrosion. So there's a technical aspect to that, which is you have hydrogen and oxygen on the same side, potentially, and what that causes is a reaction. You've got a catalyst there, and that causes a corrosion of the carbon on either side. That reduces the active area available to do your electrochemical reactions, so that reduces your power. So the way that people have done avoid this is you purge, which basically means you have to have a nitrogen tank. That's what we do in the lab at least. You have a nitrogen tank and you flush out what's on the anode side, on the hydrogen side, and then you avoid this issue. We're trying to implement that in a real system. Obviously, you don't want to be having you don't want a nitrogen tank and a hydrogen tank in the car. So people are purging obviously with air, but air has oxygen. So then there's major issues like how much oxygen is acceptable on the anode side. So that's the major issue.
So what are the electrode materials?
The electrodes.
Materials.
Um, so you have there's a platinum, there's carbon supported platinum catalyst.
Platinum is catalyst. Or
Yeah,
maybe
so carbon
one
supported.
side.
Yeah, on both sides.
Both sides.
Yes. Okay, and then the power density solutions. So I'm just going to go over one topic on each of the words. So then the power density
We've
solutions.
got 5 minutes.
Okay, thank you. It's taking a lot longer than I thought. So power density solutions, for example, are changing materials. So you have the graphite on the left, that's what most research fuel cells use. That's what we're using in my research. But the problem with those is they're really thick and they're very difficult to work with. So we have to use 2 per cell. And with the metal ones, if you engineer them correctly, you can use 1 per cell. I won't go over the details as to why, but basically that massively increases your power density. So what, as an example, the stacks that I'm working on, in 4, we get 2 to 3 kilowatts out of the stack that big, and Nissan gets 80 kilowatts out of the stack that big. So these are, you can literally transform these numbers into relative power density.
It mainly surface area.
Sorry?
Is it mainly surface area?
It's the volume. So
No, the reason why the stacker performs better from the same is because you create the surface area through etching.
no, it's because within the same volume you can have more cells. Yeah.
Yes. So increasing the surface area.
Alright, now can we hold on to the questions so that when it comes to the question section? Sometimes I know the floor is beautiful, but yeah, let's not interject much so we can get the floor of the presentation. Please. Jazakallah.
Okay, so now it's manufacturing, which is what I'm doing. And so just a quick comparison of where we are with engines and where we are with fuel cells. So with engines, how long does it take to make one engine? So it takes about 30 seconds to 2 minutes. So if I go to the Ford plant in Dagenham, about every 40 seconds there'll be an engine coming off the line. For fuel cells, it will take anywhere between 2 hours and a couple of days to make a single fuel cell stack. And so then, okay, let's have a look at the number made. So one company, so again Ford, will make millions of engines per year, or at least 8 million engines per year. And fuel cells, the biggest fuel cell company makes no more than a few hundred, maybe pushing 1,000 if they're lucky. Lifetime, again, we've already talked about that. So engines, you've got 5,000 hours. Fuel cells, Nissan and Honda claim 5,000 hours, but again, that's lab conditions, so we don't really know. Cost, and this is real cost numbers now. So how much does the engine in your car cost? Well, it costs about that much per kilowatt. So 100 horsepower, it's about, let's say, 80 kilowatts. So you're paying a couple of grand. And for fuel cells, it's much, much more. And then infrastructure, so how do you go and fill up these things? You've got loads of infrastructure for engines. You can go up to any fuel station. And fuel cells, I think in the UK there's 3, maybe 4 refueling stations, and most of them live water.
Come on.
Okay, right, so this is actually what I really wanted to talk about with my PhD. So what I'm doing is so there's currently an approach to making engines, and the idea is to, how long have I got left?
2 minutes.
Okay. My research is to abstract that approach, so what information do they take from the engine manufacturing process, and bring that back down to the fuel cell level and figuring out if you can apply the same approach to fuel cells and building that knowledge base. So this is the kind of overall model. So bringing in product information, processing that, and hopefully spitting out a factory at the end of it. And there's a bunch of rules and stuff and mapping. So what I wanted to show was very quickly show an approach, which is to say, I have fuel cell information, I transform that into knowledge, so map this information, and then once you have the knowledge, you can start to inform things like equipment selection, you can re-describe the sequence for a process, etc., etc. The final few slides. The real problem is engines are still too good. That's why we're not seeing fuel cells today. That's the power density and the specific energy and specific power of engines, and they are really, really good. Like the best fuel cells struggle to compete with that. So what you get out of an engine is a great acceleration and great top speed, and you either get one or the other with other systems. So thank you for listening. I hope that was informative, and sorry it wasn't better organised.
That's okay.
So,
Yeah, Morasa, thanks so much for the wonderful presentation. Quite insightful, and a lot of good questions as we're coming our way. But we still have a bit of time, so we can take some few questions.
Absolutely, yeah.
Yeah.
A couple of maybe a bit more long-term questions, kind of. Standard question is probably how far away are we in terms of rough numbers to production level cars? Because I assume the cost and that sorts of stuff is not really an issue, because as soon as you go into production, it's going to go down massively, right?
Yes, okay, so Hyundai have started selling their car in the UK.
Fuel cell
Car. I think they've sold, I think they brought to the UK maybe 5 or 6. Grand total. Funnily enough, it got stuck at, I spoke to the guy actually, and he was saying it got stuck at the, on the port. They couldn't get it through customs basically, because they couldn't figure out what it was. I mean, it looks like a completely normal car, but there's no categorization for a fuel cell car within government or whatever.
Regulations.
Yeah, so they couldn't bring it into the country for 6 months. So basically there was about 5 fuel cell cars sitting on, I can't remember what port it was, about 6 months, yeah. So yeah, they're trying to do it. I think the first country will be Japan, and they have a plan. They have a real plan to say by 2020. So they've got the Olympics coming up then. They're building the infrastructure. I can't remember the numbers off the top of my head, but they're going to have a significant number of fuel cell refueling stations, and that's a joint effort between government and companies that are equivalent to Air Products in the UK or in France. So there's a proper plan in Japan to do this stuff, and they're really, really far ahead.
That's amazing.
So yeah, so they have a fuel cell stack ready to go pretty much, and they just want to put it in a car and do it sort of thing. The other place where you can see it likely to happen is California. So they're really doing good over there. But my personal view is automotive is completely the wrong place to start applying fuel cells. It's the most difficult industry because you have so many laws, you have so many regulations, you have safety, you have so many environmental conditions. So trying to apply it into the automotive sector is the most difficult you could do. If you can solve that problem, you can apply them anywhere. But I would say a good place to do it, for instance, would be to do just stationary power, just have off-grid power. So for instance, at Jalsa, we have these big tall lights with diesel generators in them. Replace that with a fuel cell. That's a great place to apply fuel cells. It's a nice constant load. It's really easy to do. So that's where I would see it really happening. Yeah.
And also the incumbent or the contractor is not as efficient.
Sorry?
And also the incumbent or the contractor, diesel generator is not as efficient.
Yeah, it's not as efficient. You have to refuel it. It's loud. It's smelly. It's horrible. It's Yep.
So the main advantage of this one is that it's environment friendly. Is there any other advantage?
I think that's a really difficult thing to answer because, okay, so if I go to a fuel cell conference and there are opponents to the fuel cells or whatever in this conference, they'll say, hydrogen is dirty because where are you getting the hydrogen from? Well, you're getting it from hydrocarbons. So how are you getting that out? So you're going to have to do some dodgy process maybe to get this out unless you use maybe an electrolyzer. So the argument for the fact that they're green is quite easily lost. For instance, things like recycling. How do you recycle these things? An engine is really easy because it's a block of metal. So I think that's a really hard thing to properly.
So why would you want to promote it then?
Because it's still better than engines in the sense that they're a hell of a lot more efficient. So the energy you put in.
When you say efficiency in terms of
Efficiency of the system. So if I have an engine, like I said, for 75% of what you put into the engine will be lost as heat. In a fuel cell, about 40%, 45% will be lost as heat. So it's double the efficiency. Yeah.
and what does that efficiency give you?
So what do you mean?
Like what's the benefit of the efficiency? When you say efficiency, it's quite vague.
Yes.
Yeah. So I mean.
So why? So for
So
instance,
why? What,
so both of these systems essentially you could say they use hydrogen.
yes.
So combustion uses hydrocarbons and they combust it,
Yeah.
and fuel cells use the electrochemical approach to releasing that same energy. So if you have 1 kilo of gasoline and you process that and you put it into an engine, you'll go, let's say, 100 miles. And you put that same thing into a fuel cell and you get 200 miles.
So what it means is that you're looking at it from an economic perspective in terms of efficiency.
Yes. Well,
It's not economical. It's more expensive actually. But I think overall, yeah. But if
Can
you're
we let
going to
the speaker-
space,
Can we let the speaker talk?
yeah. Sorry, I lost my train of thought there.
Yeah. What I'm saying is like, so are you looking at it from an
I
economic
think
perspective?
there's a whole aspect to that. So fuel cells will only release water, whereas engines you're emitting particulate, CO2, and all this other stuff.
Yeah.
So why I say I'm a bit hesitant to kind of paint the brush and say fuel cells are green. I think that's a bit too much of a sweeping statement.
Yeah.
But I will say they are better than engines in the green sense. Does that help? We can talk more about it
Yeah,
later.
alright,
if
okay.
you want. Yeah. And if you want.
yeah, so
Hold
I
on,
missed,
I think let's go by the rules, right? So let's see who's gonna write you.
Yeah.
Yeah, so I missed some part of that discussion, so you might have answered it already, and I actually needed one of the slides from before, but that's okay. I think we've swapped, right?
Yeah.
Yeah, so you showed the graph at the end, and that was
The energy
showing watt hours per kilogram. So we're talking about the energy per kilogram of fuel.
That's the difficult part. Okay, different academics will cluster different parts of the system and call it an energy density, which is what's really hard to define. So some people will say hydrogen is more energy dense per kilogram than fuel, like than a combustion engine. But here you're comparing a fuel to a device, right? So some people will actually do that. They'll say hydrogen versus combustion engine, right? And there's papers that actually try and do that comparison, but you can't. So what are you actually comparing? So what I say you compare, you have to compare the whole system, and then you have to think about, well, what is the system then? Where are the boundaries of the system?
My basically question essentially was, and again I might have missed part of your answer,
yes.
apologies for that, is what is the bottom line? Like why
Right.
use, or when can we use fuel cells where it is, forget about the environment for now, but it is economical, it is viable. What are our measurement comparisons? What are we measuring?
I think if money wasn't an issue, we'd be using them now, right?
Okay,
So
because
they are, for the same amount of fuel you feed them, you're getting more out of it. You're getting a better distance, you're getting more electricity, whatever you want to say. They are a more efficient, even as a system,
Yeah.
they're more efficient. You get more bang for your buck effectively. That's the sort of.
Okay.
All right.
I'll let you
Okay.
there. We can have a chat later.
Yeah.
How do you refuel them? I mean, if you have to, is it
Yeah,
the
so
same?
it's very, very similar. So you go to one of these dodgy hydrogen refueling stations and open a cap, stick the nozzle in, and off you go. But then, okay, in gasoline and diesel, you have a liquid. Liquid is easy to pump, and hydrogen you have a gas, you have a compressor. That in its own is quite expensive, and not only that, you're dealing with 700 bar on the fuel cell cars, 700 bar. So in the fuel cell refueling station, you have 800 bar. So you're in your hand, you've got this thing that can go off, which is really scary. I think it's best not to inform the public about you're holding a bomb in your hand. Yeah. Can we stop recording now?
You only get lucky if it doesn't trigger. Yes.
Is pure hydrogen gas the only way to transport it? And the second part of the question is, how do you manufacture it? What is
The fuel cell.
Yeah.
Okay, so hydrogen is not the obviously only carrier.
But
So-
pure hydrogen gas, or can the hydrogen be mixed in something?
Oh no, you want for PEM fuel cells, you want it as pure as possible, like 99.999% or something ridiculous. So what happens usually? So okay, there's different ways, there's different approaches. So there's a company called IGM Power, and what they do, they have an electrolyzer on site. So you just come in with distilled water, put that in. It's a reverse fuel cell basically. So you give it power, and it produces hydrogen and oxygen, and you use that hydrogen to fuel the car. So you're using water in that sense. So that becomes your carrier. So it's a lot easier to transport water around than to transport hydrogen.
What's the long-term view of how hydrogen will be manufactured?
Okay, so there's a really nice blue sky model, which is to say you have something called the hydrogen economy. So you have this circular system where you're plucking energy from the wind or solar or whatever, and when the grid can't handle it, as it can't at the moment. So I don't know if you're not aware, but at the moment, when we have an excess of energy being generated by renewables, we turn the renewables off, and then we pay the people who own the renewables for turning them off. So it costs the grid more money to own renewables than it does. It doesn't save them any. It costs them money to have it because they have to keep turning them off and then paying people to turn them off. So the idea with that would be to say, instead of turning them off, let's produce hydrogen with it. So you stick an electrolyzer at the bottom of the wind turbine or at the solar on the solar panel, and when the grid can't handle it, you produce hydrogen, and that becomes your carrier of energy. Usually it's a carrier of energy, and you distribute that around. That would be the model for how you would do that.
All right. Okay. Yeah.
He had a second part to his question, which was how do they make them at the moment? How do they make fuel cells at the moment? So different people have different approaches, but majority of it is manually done. One of the things I'm looking at is to try and use a robot to do it, and some people have done that, but it's really, really hard because you have very floppy components which are very sensitive to humidity and this and that, and it's a nightmare. So, yeah.
You might have answered this before, but do you have to fuel the fuel cell as often as an engine, or is it something?
So it depends on how big your tank is.
Okay.
Right. So 5 kilos of hydrogen will get you 250 to 300 miles. But 500 kilos of hydrogen at 700 bar is probably about that big, that deep. You're kind of looking at space about that big. And that's a big cylinder, so it's rounded on the corners so it takes a lot of space. Whereas your car will have a 60 litre tank, which will be considerably more compact, and you can design that how you want. So fuel tanks are designed many times after you've designed the car, because you have some space left, and you think, okay, I'll just kind of go around these corners and I can build the tank I want and fit it into that space. So
it's basically half half time as much as you would have to go to.
It depends on the pressure. I think that's the major thing. You think, yeah, PV, MRT.
All right. Yeah.
Um,
That's about the last question.
So, also you
Time.
mentioned about the efficiency, that, so that's, theoretically speaking, an engine that works on thermodynamic principles has is limited, but with fuel cells, theoretically can be very close to 100% efficient, as long as just looking at the energy conversion from chemical to electrical within fuel
Right, so
cells.
the absolute conversion is 55%. You're not going to get that much better than that.
Really?
You're not going to get 100% out of a fuel cell. You're not going to get close to 100%.
Okay, alright.
Yeah.
So even taking that, okay, so you're going from 25%, or actually some engines, you really push them to say even go to 30%. But that's fine as far as the engines are concerned with the fuel cells. But obviously, producing the hydrogen through whatever process will also have some inherent inefficiencies
Yeah.
in there. So, taking two examples, so one could be you use a hydrocarbon and then you somehow chemically reform into whatever to convert it to hydrogen, or you mentioned the example of electrolyzer, which is effectively just using that electricity on site to do it. So when you look at the whole sort of, as a concept in cars of well-to-wheel,
Yeah.
efficiency, system efficiency, then where does the comparison come to when you're again comparing?
I think it massively depends on how you produce the hydrogen.
So,
if you, for instance, use an electrolyzer, you're pretty much doing 0.6 times 0.6.
so that's 36%.
Yeah. So that would be the well-to-wheel.
Okay.
But do you really want to? If you then start to think about well-to-wheel of combustion engines, I really don't think that's a fair comparison, because you're not having to do much to the fuel. You just basically suck it out of the ground, put it in a tank, and off you go. And I don't like that comparison, because it's a free fuel. You're not having to do that much. You process it a little bit, okay, fine. You're doing it on a massive scale. That's why it's so. I mean, it's cheaper than water, literally. So, yeah, there have been a lot of work to do with well-to-wheel, and hydrogen, fuel cell cars don't come out very well on this comparison.
Because isn't that really the right metric to look at? And the reason I'm saying is that the starting point for both of them is always a primary energy source. So you need oil for both of them. In one case, you're using oil.
You don't need oil for both.
No, in the sense for example, if you're taking thing of electrolyzers, because hydrogen is a carrier, you need energy to generate hydrogen in any case.
Yes.
And where does that energy come from? So either it could be renewable, in which case it's good, but if it's say even an electrolyzer, that means initially there was a power plant that ran even CCGT, 60% efficiency, transmitted electricity, which was used for electrolyzer, which produced hydrogen, which might have been transported. So when you look at the whole
so
chain,
if you were going to make hydrogen from an electrolyzer and use fossil fuel sources, that's really stupid. You just won't do that, because you could use the fossil fuel directly and make hydrogen.
and you're saying that, so was it
So
the conversion efficiency of that?
I don't know, but it'd be definitely a lot less than going from putting it into a turbine, producing the electricity, transporting the electricity, putting it in an electrolyzer, getting the hydrogen out. I mean, yeah, that's just crazy.
All right, okay, thank you very much, Marasa. It's been a wonderful presentation. The rest of the conversation can continue after.